All right, so on to our last topic for data simulation that's kind of following up with power. So I wrote this using R, and all of these slides will be uploaded on the OSF page after we're done here because I forgot last night. But what I'm going to show you is the faux package written by one of our very own, Lisa DeBrine, and how to turn that into a power analysis. So we're connecting both making fake data to running the power analysis. So you can take this kind of structure and use it on your own. So part of our proposal workshops hosted by us. So the packages I'm going to use for this demonstration, faux, which is the word fake in French, dplyr, because I live and breathe dplyr at this point in my life, tidyr. I may not need tidyr anymore, but I originally had it in there. And then I'm going to do a multi-level model simulation. And then there's a separate workshop that I recently gave to the PsycRStats group if you need help with MLMs. I also have some other tutorials that I can share. So I tried to keep this in the middle. I shoot for the middle here of complicated. Lisa also has an amazing set of tutorials on the faux package website. So if you want more info, she has some really great walkthroughs. But since a lot of our study designs use MLM, I kind of was like, here's how you might hack one of those together. Okay. And so the parts that you kind of have to work through when you're coming up with these simulations, with the ultimate goal being a power analysis, this is just my made up list, but you kind of have first, okay, what are the variables I want to use and do, right? So I want to make up data based on these variables. And between that and the next step is knowing what those data should look like. And that is kind of hard sometimes without pilot data. If you have pilot data, this is infinitely easier, or previously published data, but just even knowing what are the means that you expect, right? So what is the mean of this variable normally? That kind of thing. Okay. So then we'll create fake data. I will admit that I'm not super great at simulating data totally from scratch. My students can attest that I often make up data that is too good. So I went through this process last night and would like look at the results I was getting and was like, wow, I made that data pretty much perfect. Let's make it messier. So it is kind of an iterative process of making sure that you're simulating something actually feasible, meaning like I would actually could potentially get this result. And I still didn't get it perfect, but I got tired. So there is a little bit of like kind of, running it once, looking at the answer and coming back to the beginning and messing with the numbers. If you have like all between subjects designs, this is much easier. So I went with a mixed design where I have some within factors and some between factors, since that's moderately common for multi-level models. And that way we could kind of see like how you would do each piece, but you can separate them completely and do all within, all between, or all predictors, meaning continuous variables. So the faux package is not limited to only categorical predictors. Okay. Then you can figure out the analysis once you have some of your fake data. From that, how do I get the number I want to save? And this sometimes is tricky in R, figuring out where that p-value is actually saved in the output and digging it out. Okay. This is a great question for ChatGPT, though. It's really good at telling you, like, using this package, where is the p-value saved? And it actually sometimes gets pretty close. Okay. Then adding a loop. I don't care what people say. I will live and die by the for loop. Okay. And I will raise my hand about it. And I don't know how to turn that off. So I think Savannah can maybe turn it off for me. Lower hand. There it is. Thank you. I will live and die by for loops. I started learning coding many moons ago and did everything in Perl originally. So I live for for loops. I write a lot of Python for loops. So no matter what R people say, you can write a for loop. It's fine. There are other packages that try to automate this a bit more. So there's the SimR package, which is pretty good. I took a tutorial on it once, and that really helped me out because I think it's a little overwhelming at first. And then there are ways to do this with the apply family, but I just find loops so conceptually like very clear. So hopefully they're clear by the end of this. And then creating a summary. Okay, so I'm gonna walk through each one of these steps. So figuring out the variables, I'm just making something up here, and I actually picked something that my research team has done with Jeff Pavlicek, who I think I talked about before, who does all this really cool research on meaning in life and the predictors of meaning in life. So this is your very traditional like positive psych field. And what we've done before is we've tested people multiple times. He actually did 5 times a day over several weeks, but that was hard to write code for. So I'm going to do a couple of times time periods. And so that's a within subjects control variable, right? So I want to control for time. And I'm going to measure stress because I was writing my grant yesterday and then see if that predicts meaning in life. Okay. And I think I actually made it positive, and I probably should have made it negative now that I'm like reflecting on these results, but you'll get the idea. Okay. Now, to make this more PSA-ish, I added countries, which is our between subjects nesting variable. Okay. Now, Lisa has a separate tutorial specifically on multi-level models, but I wanted to do this in kind of a simpler way. So this is a way to kind of build some of that data, but she has a way for you to control even more of the facets of those analyses. Okay. Now, the package itself has a very cool interactive use function. And so if you're kind of struggling, I actually suggest you start with that. Now, I cut and pasted the output because you can't quite make interactive work with slides. But if you run the interactive option, it will ask you, how many within subject factors do you have? So I have 1 for time. And then but then I was just testing this out. So I said that there are 2 within subject factors called cheese. There are 2 levels of cheese, good and bad cheese, right? 1 between subject factors. So it literally will like walk you through a categorical style design. Okay? So if you don't have any categorical variables and you only have predictor variables, you can't use, you wouldn't use the interactive function. But it did allow me to make the whole design. So what you end up with is sort of the parameters that you expect to have for those groups. So I've got beer with good cheese is a high mean, right? Beer with bad cheese, right, is a lower mean. So I added all the means and standard deviations. But so I recommend starting there. Just try testing it and see how it feels. But for a fully reproducible report, we can actually type out all of these assumptions ourselves. Right? The cool thing is that it will give you a plot at the end so that you can make sure what you did makes sense. So in our example, the names of the factors didn't quite print, but we've got beer and good cheese, right? Beer and bad cheese. I'm sorry, this is beer. This is water over here. So we kind of you can see the means and see if that's a pattern you might expect. Okay. Now, to do this in the simplest way without having to declare everything, if you have pilot data, the SimDF function, this is what I use actually to simulate data for my class so that all the students get a slightly different version of the same question. This does discourage copying each other's answers because they have different data sets, but it also, as a teaching tool, allows me to say, your answer is going to be different. Actually, look at your output. Okay. So what it does when you do SimDF, this is our same Palmer Penguins data set from before, is it will simulate all of the continuous variables. So there was a couple of categorical variables in that data set. I would have to do it slightly differently to get those in there. I'd have to use the sim design function, but it will simulate the same covariance structure, meaning that the data columns still have the same correlations between them and have a similar data style, if that makes sense. So if it has a similar min and max and kind of distribution. Okay. I don't know why it decided that year needed to be a float with decimals, but we could go back and fix that. But if you have pilot data, SimDF is magic. And especially if you don't have any categorical variables. But you can take SimDF and then add the categorical variables to it in the way I'm about to show you. So we can, you can kind of mix and match these designs together. Now, that does make the assumption that pilot data is representative of the final data, but I'll say it again, all power analyses are wrong, some are useful. So all of this is a lot of guessing. And any one of these numbers being wrong will essentially could mess up the power mess up the power for later, but that's okay. The movement behind creating power analyses was to be more realistic on what actually should be necessary. I would say people still use them in ways that are like moderately questionable, but having bad guesses is something that you will always have. All right, so instead of using interactive, let's do it programmatically. Okay. But I also recommend interactive heavily because it makes it a little bit easier than the code. Okay. So I'm going to start by creating the variables. Okay. So my within subjects variable, you will build it as a list. Okay. This is the variable name. Okay. So this is the label that you would call the whole variable name, and this will be the column name in the data set. And it should have 3 levels, pre, middle, and post. Okay. And that is a within subjects variable, meaning that each participant will have one of those scores. For my between subjects variable, I'll have country, and I just called them 1, 2, 3, 4, 5. Okay. And then, if you were simulating how many countries you needed, you could test this with 5, with 6. You could add more to this as a way to test the number of necessary clusters, for example. Practically, I would say that is not something we spend as much time looking at in a sense, because there are limitations that we have, right, with how many countries we can get. Now, slightly harder. Let's make the means. Okay. So I am making the average dependent variable score. Okay. I'm imagining this as the purpose in life short form because that's something I've worked with a lot. That data ranges from 1 to 20. And so I made up some means for meaning in life for pre, middle, and post. So notice here that these names need to match. So pre, middle, and post here are our variable names here, okay, with our between subjects variable being the row names. Okay. So you're creating a little data frame basically of the means where between subjects is rows and repeated measures is columns, which is the tidy, the wide format tidy verse, right? If you have 2 repeated measures variables, it's a little bit trickier to build this data frame properly. And then I recommend reviewing Lisa's example, but if you end up there, I can also help you do it because I figured it out last night before I realized the country was not repeated. So I actually started doing the tutorial wrong, just to show you that all power analyses are wrong, but some are useful. Okay. Now these numbers are totally made up. What you would fill in is the numbers that you might expect to find given what you know about your field. Okay. So I could say that our pretest, we have some variability between countries. Meaning in life definitely varies by country. I manipulated these numbers. I originally made my fake Finland, which is supposedly the country with like the highest happiness scores, much higher. And then I realized I was really messing up some of the covariance structure, so I changed it back. But let's just say everybody starts at, the middle of the data set. Some go down, some stay the same, some go up. That's normal. And then if I expect, maybe regression into the mean, or some go up. So, I just kind of made up numbers here. If it was my own data, what would I expect to find? So meaning in life scores are fairly stable. They are heavily related to stress, unsurprisingly, in a negative way. But what we found measuring them over the time is that they tend to kind of cycle up and down. Okay. And then what especially Jeff has tried to do, is figure out what causes those cycles, right? And how do we promote clinical interventions that can make people not cycle so much, right? So with that in mind, that's how I made up the data, is that I expect these to kind of cycle, where on average, if countries act like people, what we would see is that it tends to go up and down. So I have some folks who never change, one country, and then this first country has like that up and down cycle. So that's how I came up with those numbers, is the patterns that I have seen in our data before, is that we get this sort of cyclical effect. Now, when you print that out, it should look like a box of means, right? So here, and this is how you might know that you've like labeled them wrong or flipped them, right? Or did something incorrect. So it needs to line up with the expected between subjects variables and the expected repeated measures variables. Okay. So if you accidentally did pre, middle, and post as a row instead of the other way, it'll explode. So this is our means. The other thing we need to make up data is the standard deviation. Standard deviation here is normally between 1 and 3 points on the scale. It's not very high on a 1 to 20 scale. And I don't have any preconceived notions about what I should expect by country or by pre, middle, and post. In my fake study, we're not doing an intervention, so I don't expect them to go, the standard deviations to get smaller. I don't expect them to get larger. I just kind of expect them to stay consistent. But it feels wrong to make up the data where they're all like 2, which is one thing you can do. So I use the rnorm function here, which generates a random normal number. So it's like, give me 5 random normal numbers where the mean is 2 and the standard deviation is 1, so that I can get some sort of unexpected noise, because that's truly what should happen. Right? And so what I've got for each country is a different set of standard deviations. Okay. But in general, it kind of hovers in that 2 range. So sometimes they're lower, sometimes they're higher, but that kind of variability is helpful because that's truly what you're probably going to see, right? There's always probably more variance than you expect. Right, so we got our means, our standard deviations. The trickiest part to me is the correlations. Okay? Anytime you have repeated measures data, so if you have totally between subjects, this part doesn't count. Doesn't matter. But anytime you deal with taking people's numbers more than once, you got to account for the correlation between measurement 1 and measurement 2. If you're taking 2 kind of unrelated concepts, I tend to tell people to estimate that correlation as 0.1 or 0.2, which is the general CRUD factor that we see with correlations. This is the, I know Daniel Lockins has published some of this recently, but the original paper is the Voodoo correlations was its nickname. The real paper name is something else. But basically they were able to show that dead fish will give you a correlation of like 0.1 or 0.2. So when people ask me, what do I guess if I don't know? 0.1 and 0.2 is sort of a nice range for things I expect to be uncorrelated. Repeated measures data that you expect to be correlated, 0.5 is a good guess. Okay, so those are some ideas for you. I fully expect my pre and middle scores to be heavily correlated across time. So again, I'm making up one number. I said pre to middle should be correlated at 0.7. This is a very common. It actually is probably a little higher than this, but I made the data too good. Okay. So make up one number where the correlation is 0.7, but the standard deviation is 0.1 or so. All right, I can't see the chat. Thank you, Kaya. So this is a correlation table, the upper half of a correlation table. So now we're doing pre to post. So my pre to post maybe isn't quite so high. And then middle to post. Okay. So I might have actually considered switching these 2 numbers. So I'm making up some random numbers, hovering that 0.7 to 0.5 range. The idea here is to build it like the upper half of a correlation matrix. And so that's why it's in this triangle format. It's to help you think about that. So pre to pre is 1, so I leave that one out. Then we would do pre to middle, pre to post, and middle to post. Okay, so you're building a little correlation triangle to put in there. If you don't know, you can skip this step and just say R equals 0.5. It's not a bad guess. Okay, so you can actually just put in one number in this part. All right, so take all that together. Let's make up our fake data. SimDesign is the function that has between or repeated components to it. At the moment, I don't have my stress score at all. And I'll show you how to add that here in a minute. So I say my within subject variables within, between subject variables between. Give me 20 people per group. Okay. So with a between subjects design with 5 countries, that gives me 100 participants. And then, so this N is like the N per group. Now, if it's all within, it's going to be 20 because it's N per between subjects group is probably a better way to say this. Here are my means. Here are my standard deviations. Here's my correlation matrix. You can type them in right here, but then it becomes this like unwieldy function to read. So I'm also doing what Lisa does. So she shows you how to build this like one step at a time in the same way. So that if you go and look at the help, it's not confusing. Give me one dependent variable. It's going to be called meaning. One ID variable. This is actually the default, but you can call it something else if you'd like. So you get a subject ID variable. And then this argument here, long equals true, puts it into long format, right, where there's one measurement per row, which I wanted because I'm doing a multi-level model here in a minute. This is the first time I did this where I figured out I did it wrong. So the plot's very helpful, but now I can see this kind of cyclical effect. It goes down and then up. This one stays the same. Excuse me. This one's going up, down and up, and then up and then down. You can tell that I've varied the standard deviations. So that plot there, I think the error bars are actually like 2 standard deviation. It might be kind of a confidence interval. I can't quite remember off the top of my head, but either way, it's showing you kind of nicely like that they have different variances, which I would expect in this design. Some of them are probably a little too small, but this is a simulation run, so this is not what it's going to look like every single time. But this is the general picture over many runs, what I might expect this data to look like. Now, I need stress. Not really. That kind of came out funny, but I am done with the stress this week, hopefully. But I need that variable in my data set because right now, all I have are the first 3 columns. I didn't show it to you yet, but that's all that's in there. So I am adding the stress variable. So this is a function that she suggests using. So I'm going to mutate, meaning create a new variable. I'm going to call it stress because it's what the variable name should be. rnorm pre. So rnorm for the rnorm function can make up a random normal variable. Can you do other ones? There's actually an rlikert one as well. So that's really cool if you have expecting Likert data. Truncated normal Poisson, like she has a bunch of functions in there for creating different types of data sets. We're going to base it on Y. And so the pre here does not, it stands for predictor. So we're making a predictor variable based on Y with an R normal distribution. The mean of the stress scale that I remember using, the perceived stress scale, is 10. The standard deviation is 2.5. So these arguments here are the same arguments we've used before, except for the last one. Okay. So base it on Y. The mean is 10. Standard deviation is 2.5. This is the expected correlation. I have it kind of low because I kept making up data that was way too good. So, you know, I should have pulled out some real data to look at too, but let's say the correlation between stress and meaning is actually 0.1. Now that's just the raw correlation. That ignores all of these other factors, right? The repeated measures component, the differences between countries, like this is just the straight correlation between these two variables. So it adds me a column out here based on Y, which is our meaning score. And then I made time numeric because in our research, we tend to treat time as a numeric variable so that it can be continuous. And the way we actually measure this is the time since start. So we take the time that they started the study and then subtract the time that they completed each step so that we can treat time in this sort of non-discrete function. So I made time a continuous variable here, but I didn't want to estimate it as continuous because it really technically isn't. This little note here is what you're writing in here, right? So you got mu, which is the mean, standard deviation, and R. And then I just printed it out so we could look at it. So we have 3 rows for each participant. Oops, sorry, that makes it long data. They're in country 1. They have 3 time measurements. Here's their meaning and life score and their stress score. Now, if you know that the data is not going to be at this level of precision, meaning this many decimals, you can also like round it to truncate. That'll also make it more realistic. I don't know if that's super important, but FYI. And then there's a function that that Lisa has that is called messy. And so it allows you to simulate a random or specified type of missing data, which is super useful for teaching. So when I teach people factor analysis, especially, people get bored when they're taking scales. And so they tend to skip items here and there. And so I can make it messy in a certain way. And so it allows you to simulate missing data. So it's a pretty cool function. Plus it's a fun name for a function. All right, so I have my data. Can I put it into an analysis? So for this analysis, I'm going to use LME because I'm attached to an LME for reasons I don't even remember anymore, but Lemur and LME4 work fine as well. I'm going to say that meaning is predicted by stress and time. Okay. I'm using time as a control variable here, and then just using stress to see. My random variables are which country they're in and the participants. So I'm controlling for the fact that some participants have higher meaning, some have lower meaning, same with country. And my data frame. And so this step really isn't to see if it's significant or not. It's mainly just to think about like, did I actually get the analysis and the output I was expecting that I would use to make my decisions, right? So it's just a lot. And this is where I was like, wow, I did that really poorly. My problem was that I kept making time too good. And so it was sucking up all the variance, so to speak. So I was fiddling with the numbers until time came down to the number I expected. So this looks like what I might expect. 20 participants is not really a good degree of freedom for a small effect size. And then I don't know why it's not scrolling. The slide should scroll, but there are here. Can I make it smaller? Nope, of course not. I also told it to print the R squared for me. I usually try to print the effect sizes just because like I said, I have a bad habit of making things way too good. And so I usually am trying to bring the effect size down to what I expect it to be. Okay. So right now, my model effect size is what I'm expecting it to be for stress, which is small. But my covariant, wow, what does the C stand for? It's totally gone out of my head. Forgotten. My random effects are quite good, meaning that my country variables maybe not quite, is a little too predictable. But that's okay for our example. So what do I want to save? When you're working with LME, this is how you get the stupid coefficient table. Why this way? I don't know. And this is probably why I stick with NLME, is because I know this and I forget how to get it out of Lemur. But either way, find the number you want, which is generally P. But I always tell people, before you run thousands of simulations, make sure you save as many of the numbers as you want. Potentially could think that somebody might want to see, because I do have to actually rerun a multiverse analysis because I wanted the degrees of freedom and it didn't get saved the first time. So I'm actually just going to save this whole row. My focus is stress. I told it, just give me row 2. Okay, so now I've got value, which is your coefficient. This is unstandardized B, the standard error, the degrees of freedom, the t-score, and P. So if I decide later that I want something else out of this, I could add it. Okay, so now we've assembled all the parts. I have how to make up the data, how to run the analysis, and how to get the numbers I want. This is where you can start adding in the loops. So I have a little function here called save it. I used to, a million years ago when I first started doing this, create a data frame and like to plug the numbers into. That's okay. It can be very memory intensive. So the one thing you do not want to do is create like a 1-row data frame and then add rows to it each time, because in the background, it is saving the first loop, the second loop, the third loop as separate objects, memory-wise, and it will blow up your computer. So lessons learned from Brinton Wernick, I usually now make it a list, because I can initialize a list in R and add things to it in a way that isn't recreating the list. It's just adding new pieces, and it usually will save the memory on your computer if you're going to have big data sets. If you're going to run thousands of simulations, for example. Okay? This is my new favorite way to do it. The other way you can do it is creating an empty matrix to plug the numbers into, but that then requires me to remember how many rows and columns I want. And we've already decided that I'm a squirrel, so an empty list is the best way to do this. What sample sizes do you want to run? So I made this just small for today's purposes, but you could run, 10, 20, 10, 15, 20. So how many ever, whatever unit you want to use here. So we're going to run it with 10 participants, 20 participants, 30, and 40. But because this is repeated measures, we'll actually get a power boost, because while it's 10 participants, it's 3 time point measurements. And that for MLMs, that counts as bonus. And then how many simulations of each of the variables do you want to run? It should be a big number. Like 1,000 is kind of normal, but that would take way too long. So we're going to do 10, but normally big numbers. I'm going to start here with an iterator variable. So this is just start counting at 1. Now the fun part. I love loops so much. Oh my goodness. So first loop, for sample size in N. What does that do? What it does is for each of these numbers here, so sample size starts at the number 10, it will run all this code, and then it moves up. Okay, now do everything again for 20. Do everything again for 30, and then for 40. Okay. So sample size, make your variable names. There's this really funny meme on this programmer Reddit that I'm on where it's like, stop calling your variables I. And I'm like, it's very hard for me to get over, because when I learned this using C++ and Visual Basic and stuff, that was the most common way to do things. So like for I in blah, blah, blah. That makes code very hard to read later. So make it clear what you're looping over. For sample size in N. Okay. And then for my simulation number, which number am I on? Simulation number 1 for this one, number 2, 3, 4. Okay. In 1 to sim, because sim here is a number, so this just makes it count up. So it'll count 1, 2, 3, 4, 5 up to 10. Then you take those steps and plug them in. Okay. So the first step, make the data. Okay. This is our make the data function. The only thing you need to remember to do is you're now manipulating the number of participants. So before, I just made up the data with 20 participants each time. Be sure you change that, or you're going to get the same results for every one, because you're not actually simulating different sample sizes. Okay, so we were plugging in this variable here. So give me a different sample size each time. But the nice thing is with this is that, each run is slightly different. And so the standard deviations will vary a little bit. And so one of the reasons why I say, all power analyses are wrong is because I could totally have messed up what the the pattern of the data is. But the nice thing about having these variability pieces in it is that over so many runs, hopefully it kind of normalizes out. Like, yeah, this part might be wrong, but 3 bad runs doesn't hurt anybody, right? It kind of creates this like nice set of possibilities for you that you can kind of average over. That's why you should run at least 1,000. Okay. So make up your data. Now this here, I put like 4 exclamation points because don't forget this. Plot, the default's true. And if you set this to run with like 1,000 simulations and for like, set it aside and go have dinner, it will start printing out thousands of plots. You don't want that. Okay, that'll slow down your computer and also potentially crash the loop. So turn off plot. Okay. Then you take that model. Okay, be sure you fill in the name of the temporary data frame here. And then save it. So this is our save function we had earlier. So what I do is I take save it and I just put in what iteration number it is. So because each piece of a list has to have some sort of name, even if the name is like 1, 2, 3, 4. So I just say, hey, this is save it spot number 1, save it spot number 2. This variable only is just a placeholder. Now, the only other thing I added to this was the sample size. I'm keeping track of each run's sample size as an easier way to do the next page. So I say, okay, take that row of stress and also hang on to the sample size so I don't have to think that hard later. And then you run. I also suggest starting with 5 or 6 simulations for each one so that you can make sure it gives you the output you expect. But don't believe any of the power numbers when you only run 10 simulations. Okay. So thank you, dplyr. Bind them together. Since every row is exactly the same, I can just throw them all into a data frame. So here's what it shows me. It shows me the wide variability in results that one might see when the correlation is expected to be 0.1. So sometimes the effects are larger, sometimes they're smaller. So this is giving you some nice variability. Here we're seeing the standard error. Okay. The degrees of freedom for the analysis, the t-value are important part for null hypothesis testing, the p-value, and which sample size this is. So this is just a list of runs. And this is the kind of thing that I suggest people upload as part of a pre-registration or a register report so that you have kind of how it ran, for example. I say, okay, to calculate power, group by sample size and sum the number of times that the p-value is less than 0.05, divide by n. So this here is probability. And so again, I told you I made up the data way too good. This is also only 10 runs, so less believable. But then you would look for the spot that meets your power criteria. Okay, 80%, 90%, 95%, whatever makes you happy. And then you could realize, shit, I didn't run enough people. I've had this problem too. And so you would add more into it, but then delete the bottom ones when that happens. So you're not running as many. But I have simulated studies only to figure out that I didn't get high enough in my sample size estimate. So I'm upped the numbers and deleted the lower ones. You can also make some cool power charts from this data. There's all kinds of cool stuff you can do, but I do want to leave time for a couple of questions. So I have a slide at the end that I'm required to show, and I thought this would be funny as our last official session because I kept forgetting to show it, but as always, this will be hosted online. This is a very brief tutorial, and I can find more resources if folks need them, and then obviously email us with questions. So I will hit